Hello all, welcome back. So in this today's class, we are going to design the 3-bit synchronous up-down synchronous counter using T flip-flop. So first we'll try to understand what is the meaning of the up-down counting. So what is the meaning of up-down counting means? It will perform the up counting operation as well as the down counting operation. Then it is called as the up-down counter. Right, the same counter will perform the up counting operation as well as the down counting operation, so then it is called as the up down counter operation. But one thing you have to remember, so what is the thing is that the circuit will perform right, the circuit will use it to perform the up counting operation as well as the down counting operation. But if you try to perform right at the same time up counting as well as the down counting operation, you cannot able to perform. Right, the main important point to remember here is that the moment if you are performing the up counting operation, you cannot able to perform the down counting operation, or if you are performing the down counting operation, you cannot able to perform the up counting operation. It means that the circuit will support the both the operation, but at a time only one can be performed. It means that you should have the control over the, when up running, down should be off, when down running, up should be off. It means that you should have the control over the up as well as the down counting mechanism. For that, what we required is, we required something called as the controller operation or mode of the operation. What is the use of this controller or mode of the operation means? It will decide when to perform the down counting, when to perform the up counting, right? So see that the mode controller control, we can consider whatever it may be, is used to decide whether the counter will perform the up counting or down counting operation, right? So designing of such counter is the same as the designing of the synchronous counters only, like what we have done previous classes. The same thing will be here in synchronous counter also, but extra thing we will be getting the, right? So mode control input is required. It means that we require something called as the mode operation or controller operation, right? So if we consider the single bit information, we have the two possibilities, either it may be 0 or 1, right? Suppose for example, if you consider, if m equal to 0, you perform the up counting operation. If m equal to 1, you perform the down counting operation. It means that along with your synchronous counter design, we will be having the extra part is the mode of the operation. What this mode of the operation will do means, if 0 is activated, then it will perform the up counting, it will stop the down counting. Or if m equal to 1 is activated, it will perform the down counting, it will stop the up counting. Right, now we'll try to design the 3-bit. So 3-bit means it will perform the 8 stages, nothing but the MOD-8, starting from 0 0 to 1 1 1, right? So now to represent that, 3-bit means how many flip-flops are required? As we know that we required the 3 flip-flops. Why? For each flip-flop can able to store the 1-bit information. If you want to store the 3-bit information, we required the 3 flip-flops. So which flip-flop we required? We required the T flip-flops, right? Once it is done, now we'll draw the truth table for the up counting as well as the down counting, so that you will be understand clearly when to perform up counting, when to perform the down counting. Once it is completed, we will follow the same procedure for how to design the synchronous counters. The only thing is, you need to remember the extra variable will be added here, mode, which is used to control the up as well as the down counting operation. Fine, now we have the 3-bit value means 8 possible combination we will be getting, right? First we will try to complete it, how the state will be changes from the, right, after applying the up counting operation, how it will perform the changes when we performing the down counting operation. First we will go with the up count. So if your present state is 0 0 0, what is the next state value? Up count means always plus 1 to your present state value. It means 0 0 0 means what is the next state value? 0 0 1. For 0 0 1, if you think that 0 0 1 is your present state, what is the next state? 0 0 1 means 1, right? 1 plus 1 is nothing but the 2, right? So the next state is the 2. For 2, what is the next state? 3. For 3, what is the next state? 4. For 4, 5. For 5, it is 6. For 6, it is 7. It means that up counting means it is going to perform incrementing order. Once the maximum count is reaches, it will back to the initial position. So it means that for 7, what is the up counting value? It will return back to the initial position. Now we will consider the state diagram representation or state transition diagram. Now see that this many count we have, right? 0 to 7, The same thing I have taken here 0 to 7. Now see that, right, for example, suppose here we will consider, as we said, mode means, right, we have the two options, either 0 or 1. Just for example, we will consider 0 means up, 1 means for down. It means that I have the state something like this. Right, 1 0 1, final one is 1 1 1. See, when m equal to 1, what it is going to the up count, it means something like this, right? So next, what, when m equal to 0, right? So next it is going m equal to 0, next it is going m equal to 0, next it is going m equal to 0, next m equal to 0, m equal to 0. Finally, for triple 1, what is the down up counting value? 0 0, right? So m equal to 1. The same thing here we can see that when m equal to 0, it is going to the up counting operation. Now we'll see how to perform the down counting operation. What do you mean by down counting? The down counting means highest value to the lowest value. It means that 7 6 5 4 3 2 1 0. So what is the down count for 7? Always minus 1 is the down count. If you suppose say 7 minus 1 is the 6, something like that. So where we need to start? We need to start from the largest number. Here we need to start this. So what is the down count for 7? 6 is the down count. It means 7 minus 1 equal to 6. For 6, what is the down count? Yes, right, 5. For 5, what is the down count? 4. For 4, what is the down count? 3. 3 ki 2, 2 ki 1, 1 ki 0. Now question is that what is the down count for 0 0 0, right? What is the down count for 0 0 0, guys? It means that it is going to 6, then 5, then 4, 3 2 1 0. After reaching to the minimum number, it should return back to the initial position, right? So for 0, what is the next count value? The next count value is nothing but the, right, sorry, for 0 next count value is the 7 is the next count value. See, it means that which condition we are taking? When m equal to 1, we are performing the down counting operation, right? So see that where we need to start from 7, right? We need to start from 7, right? So this is the 7. So 7 m equal to 1 sorry, 7 m equal to 1, where it is going? It is going to 6. M equal to 1, where it is going? 6 ki 5. Then 5 to 4, 4 to 3, 3 to 2, 2 to 1, 1 to 0. For 0, what is the down count value? It is something 1 1 1, right? This is the state diagram representation for the 3-bit up down counter, synchronous. In exam point of view, they might be asking design 2-bit also. In this case, what you have to take? You take 0 0 0 1 1 0 1 1. When m equal to 0, it will perform the up counting operation. When m equal to 1, it will perform the down counting operation. This is important. They might be asking for 1-2 mark question like that. Draw the state diagram for the 2-bit up down counter, something, right? So once it is done, what is the next step? We need to draw the excitation table for the T flip-flop, right? So this is the flip-flop output, these are the flip-flop inputs, so this is the excitation table for the T flip-flop. Once it is done, what is the next step? We need to draw the circuit diagram, then state table representation. So see that this is the, how many flip-flop excitation table this is? Only one flip-flop excitation table. Now, but what is our requirement? How many flip-flops are required? 3-bit means 3 flip-flops are required. It means that internally we need to write the 3 excitation table, right? If you see that, as I told that 3 excitation table means what? So 3 flip-flop means, right, we require to provide the 3 excitation table. Let it be TA, TB, TC, the corresponding outputs of the QA, QB, QC. Now what do you mean by synchronous counter? If the common clock pulse is applied to the all the flip-flop, then we call it as the synchronous counter, right? So this part is completed. Now final agenda is that if this want to work as the 3-bit up down counter, we need to find out the outputs are the TA for the first flip-flop, TB for the second flip-flop, TC for the third flip-flop. Then it will become the 3-bit up down counter, right? Now only we have completed 30%, remaining 70% is pending. Now this is excitation table for one flip-flop, right? But as per our circuit design, we have the 3 flip-flops, so we need to draw the 3 excitation table. Simple thing. How to find out the excitation table means, if you observe here, what is the present state value? Qn. What is the next state value? Qn plus 1. In place of n, you substitute the ABC, that's it. Suppose if the first flip-flop is the A flip-flop, it means that you take QA, QA plus 1. QA is called as the present state, QA plus 1 is called as the next state. For pre flip-flop it is QB, QB plus 1. For C flip-flop it is QC, QC plus 1, right? So it means that the present state values are, these are the present state values. First one is QA, QA plus 1, right? Right, so first flip-flop it is QA, second flip-flop it is QB, third flip-flop is QC. The another one I told, right, along with this synchronous counter design, we have something called as the mode of the operation. What is the use of this mode of the operation? To control whether it is up counting or down counting operation, right? So these are the present state values, right? So what is the next state values? For A it is, what is the next state value? A plus 1, right? So just here writing the next state value. So for A it is QA plus 1, for B it is QB plus 1, for C it is QC plus 1, same way, QA, QA plus 1, something like this. Now how many flip-flops we have? 3. 3 means 3 outputs. One is called as the TA, another one is the TB, another one is the TC, that's it. Now see that when m equal to 0, what is the counting it is performing? Up counting. When m equal to 1, what is the counting it is performing? Down counting. It means that if you see here how many inputs we have, possibilities 0 to 7, right? The same thing here I am writing for the 2 times. See, 0 to 7, again 0 to 7. So when m equal to 0, for this 0 to 7 we are performing the up counting operation. When m equal to 1, for 0 to 7 we are performing the down counting operation. You might be having the doubt that why I am considering 8 0, because we have the 8 count, means we are considering the 8 zeros for up counting, 8 ones for the down counting operation, right? Now how to write the next state value? If you understand this one, then writing of the next state is nothing, right? So for 0 0 0 0 is your present state. What is the next state value? This is up count, right? 0 means 0 plus 1 1. For 1 0 0 1, the count is 2. For 2 it is 3, 3 it is 4, 4 it is 5, 5 it is 6, 6 it is 7. For 7, what is the up counting value? See, for 7 the up counting value is the 0 0 0. So see that here we will be getting the 0 0 0. Now m equal to 1. So what is the first count value? 0 0 0, right? Now try to guess why 0 0 means 1 1 1 we are getting. So see that down counting means for 0 0 0, what is the next state value is the 1 1 1, as we discussed in the previous example. So 1 1 1. For 0 0 1, what is the next state? 1 means 1 minus 1 0, right? It means that you will be getting 0 0. Or if you have the still doubt, 0 0 1 is your present state value means, right? Now see that 0 0 1, what is the next state value? It is going to 0 0 1 means it is going to 0 0 0. If it is 0 1 0, it is going to the 0 1 0, right? So now what is the present state I am taking? 0 0 1. So 0 0 1 means 1 minus 1, nothing but the 0 0 0, right? So 0 0 0. For 2 it is 1, 3 it is 2, 4 it is 3, 5 it is 4, 6 it is what? 5, 7 it is, the value will be something, this value. Now once it is completed, now what we have to do is we need to find out the output value of TA, TB, TC, right? Now question is that how to find out the TA value, suppose for example. So how to find out the TA value means you just substitute here n equal to a plus 1, so that you will be finding the TA. If you want to find out the QB value means just to consider the QB plus 1, so that you will be finding the TB. It means that to find out the TA, what is required? QA is required, one more is the QA plus 1 is required. What is the QA value? 0 1. So just come to here, 0 1 means what is the answer? 1, right? Just here writing 1. Next, what is this QA value? 1 0. 1 0 means what? In excitation table 1, right? Just you write this 1. So for example, if we consider this 1, this one is 0. 1 0 means what? The 1 0 means again 1. So like that you need to fill up the entire table, right? So just by seeing the QA plus 1 value, so come to this table, then find out the value. So what is the how to find out the TB value, guys? See, if you want to find out the TB value, we need to consider QB plus 1 value. It means that 0 0. What is the answer? 0. Suppose if we take this input possibility, 1 1 means what? The answer is the 0, right? Something. If it is 0 1 means answer equal to 1. Just find the QB plus 1 value, then come back to excitation table, copy the output value to here, that's it. Right? Once it is done, next what we have to do, guys? Final thing is that we are going to find out the TA value, TB value, TC value, right? So it means that we require some logic expression, right? So to find out the logic expression, here how many outputs we have? 3 outputs we have. 3 output means how many K-maps we require? 3 K-map is required. Which variable K-map? As I said in the previous class, before the next state we called as the input, after the next state we called as the output. So how many inputs we have? One is M, QC, QB, QA. It means that we have the 4 inputs. 4 inputs. So how many K-maps are required? 3 K-maps. Which variable K-map? 4 variable K-map. Why 4 variable K-map means? I have 4 inputs, including the mode of the operation. We need to consider the 4 inputs, right? So 3 K-maps which having the 4 variable K-map. So before going to find out the K-map, first we will try to find out the minterms. That minterms we can apply inside of the K-map, so that we will be finding the logic expression. See, these are the input values, right? So what is the input value? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So let it, we will find the first, these are the output values, right? Before next state we called as the input, after the next state we called as the output, right? So if you want to find out the output expression for the TA, see that this is the SOP function, right? What is the input value? 0, right? This is also SOP, right? 1, right? So like that all ones means we need to write the all the variables. So it means that minterms are the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, next 10, 11, 12, 13, 14, 15, because SOP function. So after SOP function, see that if you T the TA, so all ones, right, in 4 variable K-map. See, in inputs what we have? M, right? QC, QB, QA, right? 4 input variable. So they here they have taken, instead of QC they have taken Q3, Q2, Q1. Like this also you can consider, right? So if these consider something like this, the first value should be M, second value should be Q3, next value Q2, Q1. But if you consider something like this, how to represent in the K-map means first value should be M, next QC, after that QB, QA, right? So don't forget to remember this. This is important to be remembered. Don't try to like something here QA, QB, then QCM. This is completely wrong, right? So if all the cells are filled, what is the answer? 1. So we have obtained the output expression for the TA, right? The same way we need to find out for the TB, TC. Just how to find out, I'm not going to explain again here. Just to find out the minterms for the TB, again you find the minterms for the TC. TB means what? This one, right? So this is 1. What is this answer? 1, 3, 5, 7, then this is 8, then this is 10, right? Next this one is the 12, then next one is 14. So then come to K-map, then substitute those minterms value, you will be finding the expression for this one. Right? Now you might be having the doubt, right? Final step, how to draw the logic circuit diagram, right? So if you see this logic circuit diagram, it is little bit complex. So what I will do is I will make it as a more simplifier. So how many flip-flops we required, as we said earlier? 3, right? So one T flip-flop, another T flip-flop, another T flip-flop. So one is TA, outputs are QA, QA bar. For second flip-flop, TB, outputs are QB, QB bar. TC, QC, QC bar. This is for A flip-flop, B flip-flop, C flip-flop. If the common clock pulse is applied to the all flip-flop, then it is called as the synchronous counter, right? Now what is the TA value we got? This is the TA, right? TA equal to 1, right? Just to connect TA equal to 1. Now see that you have this value, right? Here we have in terms of the Q1, Q2, Q3, but we have taken QC, QB, QA, right? You find out own K-map, that you convert this value in terms of the QA, QB, QC you will finding, that will substitute. Just for example I am explaining. Now if you observe here, this is AND gate, right? M into Q1 bar also AND gate, right? This is what? OR gate, right? So here what we are going to do here is, just I am taking the one AND gate for this one, again AND gate for this one. The output will be given to the OR gate, because in between we have the plus operator, right? So this is what? Output of the T2 or TB, right? So what is the input value here? M bar Q1, this one, M bar Q1, for this one M Q1 bar, something like this. Now see that where we have the TB, here we have the TB, right? So AND gate is required, AND gate, then one more is the OR gate is required, right? That we are connected to here. Now what is the input value? One is M bar Q1, another one is the MQ1 bar. That's it. If you do like this, this is also correct only. The same way here you draw the AND gate, AND gate. It means that you will be getting the 3 inputs AND gate. You will be finding the OR gate. So output will be given to what? TC. It means that here we have the 3 inputs AND gate. The output will be given to the OR gate. So this you just write down M into Q2 bar Q1 bar, right? M into Q2 bar Q1 bar, right? So here M Q2 bar Q1 bar, that's it, right? This is your up down counter for 3 bit, right? So like that you can design the any counter, right? I hope you understand, right? Thank you very much, guys.